here at the end, or in the middle of class last time. I just wanted to point out that we did this great job of defining these variables p and t and dp and dt, and then when we started using them, for some reason I switched all to x and y. Okay, so the point was to use what we defined. Okay, so if p was dependent, then what's a change in p? If p is a dependent variable, then what's the change in p? How do we represent a change in p? dp, right? dp. So we have p. And if time is our independent variable, then we represent a change in time as dt. So if we want p final, and we had a rate of change m, how could we compute a final value of percentage? How could we compute a final value of percentage? So work with the person next to you. This was an important idea we worked on a week ago, and it's going to be really important. So p final equals what? P final equals what? Other than, or no, yeah, p final equals what? Okay, so we should have this down. P final equals P initial plus, and how did we find dp? What is dp equal to? Plus? Yeah, not plus, right? That changes in the dependent are a constant multiple. If we have a constant rate of change, which we did here, then any change in p would be a constant multiple times the change in t. So it would be p initial plus m dt. So this was the notation we should have been using when we were doing that, making that graph. Okay. For some reason, then that whole thing I switched to x and y. Sorry, that I won't try to ever write things on the screen there again, because this is in the way. Okay, but that says p final equals p initial plus m times dt. Okay? All right, that's better. Okay. So this is how we should have been notating that whole problem. We should never, for some reason, I just went right back to x and y. And there's nothing magic about x and y, it's just the most commonly used. But if we define our variables p and t, then we should be working this way. The p final is p initial plus m times dt. The other thing was, I got a question after class, and it would have been good for me to address this. So many of you realized that we were essentially, when we were saying, let's define all of the correspondence points for this situation, we were creating the equation of the line. And so the question came up is, well, can I just use mx plus b? And so yes, mx plus b would be another way to represent all of those correspondence points. But this process that we're teaching you is essential for what's coming. You have to understand that. You have to understand this process of start with a p initial, start with a change in your independent, get the change in the dependent from m dt, and add to the initial p. That concept or that idea or that process is essential for calculus. Okay, mx plus b just won't cut it. We've got to understand what's going on with that process that we worked on last time in class. Okay, so if you've got another way to graph or think about lines and equations of lines, learn this. You've got to learn this, because when we get to the calculus here coming in the next couple of weeks, it's a crucial idea, this process that we learned, and we'll see it again today. Okay, so let's get started. So I think you read about this maybe over last weekend. I kind of jumped the gun with some of the last part of your homework for Tuesday. So actually, we'll assign it again. You get more time to think about some of those problems at the end. We want to refine meaning for dx. Okay, so the test is written for our old meaning of dx, okay? Just to let you know. So our test is everything up to what we've done today, okay? But a refined meaning for dx, so until now we've said that dx is simply a change in x, okay? And now we're going to qualify that to say that dx is a little change in x. Okay? We're going to say now dx for us means a little change in x. Up till now, it's meant any change in x, large or small, and that's the way the test treats it too tonight. That's the way the test treats it too. dx can be a large or small change. But from here on out, we're going to call this dx the differential in x, and it's going to mean a little change. A little change. And we're going to talk about why we want that today. Okay, so that's important. And then so for related variables y and x, talking about differentials dx dy necessarily implies constant rate of change. So if we're talking about a relationship between dx and dy, then it's implied that we have constant rate of change between them, and dy equals mdx. And given any change in x, the change in y will be m times that change in x, right? Super important. So if we're talking about dx and dy, that always implies that constant rate of change, that dy is m dx. Okay? dy is a constant multiple of dx. Okay, so now we're going to the dx dy language is going to mean we're going to call it the differential in x, and that's from here on out it's going to mean a little change in x or in y. Okay, so let's do a video because videos are always fun. Here we go. Nine, 58. Okay, so he ran 100 meters in 9.58 seconds. So this is the fastest 100 meters ever run, recorded by a human being. Okay, so the question is, where are we here? Next slide. Someday I will learn how to do the slides. Okay, here we go. So, Usain Bolt broke the all-time world record in the 100-meter sprint by finishing in 9.58 seconds. How fast did he run in miles per hour? So how fast did he run? Really, really fast. Okay, exactly how fast did he run in miles per hour? Nice practice problem for the exam tonight. Can you do it? I'll give you some info. There's 3.28 feet in a meter. And there's 5,280 feet in a mile. I'm going to put up, there's lots of ways to approach it. I'm going to put up the way that I set it up. And it's got the nested parentheses. What I want you to do is tell the person next to you every set of parentheses what quantity that is. In every set of parentheses, what does the quantity mean, okay? So this is how I did it. So you're going to start with 100 over 9.58, and then that times 3.28, and then that divided by, and then, so every set, what quantity does it represent? Yeah, it's right there. Even if you did it much differently, can you analyze mine? Can you analyze mine? Mine's not better than yours. It's just different. Can you analyze mine? Okay. 100 over 9.58 is, what does that represent? Speed in meters per second. If I multiply by 3.28, what does that represent? Speed in feet per second. How many feet per second? If I divide that by 5,280, miles per second. Miles per second times 60. Miles per minute. Finally, miles per hour. Okay? It's not better than your way, but it's a good exercise to look at someone else's way and analyze every step along the way. Any questions on that? Okay? Fast. How fast did he run? Fast. Okay? Did he run at a constant speed for the entire race? We just got one number, 23.34 miles per hour. So with one number, that could be nothing else than a constant speed. If you're just given one number as a speed, that has to be a constant speed, right? Because it's just one value. So did he run at a constant speed for the entire race? So it's impossible to go from 0 to 20 miles per hour instantaneously. You can't do it, or else you would die. The acceleration would be so great that you would pulverize. Okay? So all speed changes continuously. So he had to speed up from being at 0 miles per hour up to some speed. And so then what was that 23.34 then? Yeah, so his average speed for the race. Okay? So he ran many speeds during the race. So what does it mean that at 1 second after the start, he was running at 13.754 miles per hour? What does it mean that at 1 second after the start, he was running at 13.754 miles per hour? So it's not a trivial question. Anyone want to give it a shot? What does that mean that at 1 second he was running 13.754? I saw you first.
That probably was at that point in time he was going at that speed, so he accelerated there.
Okay, so now at 1 second he's running the speed. What does that number 13.754 mean? Yeah.
That's average at 1 second.
So it's average over the first second. Is that what you're saying?
Yeah.
It's average speed over the first second. Okay, so actually not what I asked, right? So I'm saying at 1 second. Yeah.
At that moment, at 1 second, if he were to continue running that speed, for every change in hours, the change in distance would be 13.754 times the change in hours.
Wow, that was really good. Did you hear that? He said if he continued running that speed, starting from 1 second, then given any change in hours, his change in distance would be 13.754 times that change in hours. dy equals mdx. I got the chills. Good job. All right. Okay. So let's talk about this. Here is Usain at the instant when exactly 1 second has elapsed. How fast is he running? This is the instant. Exactly 1 second has elapsed. How fast is he going? He doesn't look like he's moving to me. How fast is he going at the instant, 1 second? 0. We could sit here all day. He's not going to move. What is required to have rate of change or speed? What's required? A little change in time, right? So at 1 second, he's not moving. 0, right? Okay? So we're clarifying this statement. So this statement is not asking at the very instant of 1 second how fast he's going because that's 0. Okay, but if I come over here, what do you see when you zoom in? Oh, too far. What do you see about the picture? It's blurry. Why is it blurry? Is this really capturing the instant of 1 second? What is it capturing? What's that? A shutter speed, which is a very short change. It's a change in time. So we see it's blurry. So there's actually a change in time there, and that's what we need to make sense of a speed. We need some kind of change in time. Okay. So we see that So how we're going to clarify this question, what does it mean that at 1 second he's running 13.754? We're going to talk about what's called a moment. Here is Usain at the moment when 1 second has elapsed. How fast is he running at this moment of time? And by moment, we're going to mean a small change. A small change. Okay? That's different than differential. We'll get to the difference in a second. But by a moment, now we're saying, let life be blurry. Okay? So speed is blurry. So let's see the blur. Let's get a little change in time. Now we can talk about that he's actually going 13.754 miles per hour. So when we say, what does it mean that at 1 second after the start he was running this fast, we have to consider a small change in time to make sense of that. And that's what we're going to call a moment. So a moment is a small change in the independent variable. A moment is a small change in the independent variable. And we need that to make sense of rate of change or speed. Otherwise, at 1 second, we just freeze time and nothing moves. Everything's zero, has a zero rate, right? Everything has a zero speed or zero rate if we truly freeze time. But if we look at a moment in time, now we can start talking about speed. All right, so here's the difference. dx is not equivalent to a moment. dx will vary, remember dx is a variable, within a moment. So we'll have a moment, the moment in question, and then we're going to let dx vary in that. So it's like dx is small, even smaller, and it varies in the moment. Okay? So dx is smaller than a moment, and it varies in the moment. So it can vary, say, from 0 to whatever the width of the moment is. Okay? And we'll keep talking about that too. Okay, so a rate of change at a moment exists if there's a small enough interval in which the rate of change is essentially constant. Okay, so a rate of change in a moment is when the moment is small enough and we can consider a constant rate of change. Constant rate of change, really important. We make the moment small enough to the point where we can say essentially what's happening in that moment is constant rate of change. That's called a rate of change in a moment. Okay, so let's look at so then that constant rate. So if we make a moment small enough at t equals 1 second, and we get a constant rate of change, then that's what we mean by his speed at that speed of 13.754 miles per hour. That speed, 13.754 miles per hour, is a constant rate of change at a small moment of time at 1 second. Okay. All important stuff. Anybody have a question on these ideas, definitions? Okay. So let's look at in GC. So here is, make things bigger here. So here is this function f defines his distance from the start at t seconds since the race began. Okay, so I found there was a table of values that gave his distance from the start every half second or every tenth of a second or every second, and then so I did a regression. I did a polynomial regression to those points. I came up with this function which gives the independent variable is his elapsed time since the start, and then the output, or the dependent variable, is his distance from the start in meters. And so here's that graph. You don't have to put it in. You don't have to worry about that. You can if you want. So we want to get a better view of this. So we can not do that. So we want to zoom out on the y-axis to see this a little better. Okay, that's pretty good. And so what do we see about his distance from the start? We can see that he's not running at a constant. If he was running at a constant rate, what would we see for this graph? Yeah, so the points, all the correspondence points would lie in a straight line if he was running at a constant speed. And we know that at the beginning of the race, they accelerate rapidly. Okay, and so we were interested in down here around at 1 second, his speed at 1 second. And so let's talk about a moment at 1 second. So the way I'm showing the graph right now, this interval, say, is this showing a moment? Is this showing a moment? It is. It's a really large moment. We're interested in small moments, and especially the ones small enough to get us a constant, essentially a constant rate. So if you, I think you've learned this, but if you haven't, so if you hit Shift and then put a box around a place you want to zoom in on, it will do that. So what about now? Is this showing a constant rate of change? Still a little bit curved. Does it still look a little bit curved still? So let's go into, say, from 0.95 to 1.05. Let's try that. How about now? So now I'm into 0.99 or 0.95 to this is about 1.08, and you see now that all these correspondence points right at 1 are seeming to fall in a straight line. This is the idea that if our moment is small enough, we essentially get a constant rate for that short amount of time. So I'll just do one more time. We'll do 0.99 to 1.01. Okay, there we go. So here is one right here. And so to our eye, that looks essentially linear. And so we have a moment here for which we have the constant rate. How could we figure out what the constant rate of change is at this moment at x equals 1? How could we find that constant rate of change? What's that? Y over x. You agree with that? dy over dx. So what will we need to get dy and a dx? We need a couple of points, right? So we would need a couple of points. If we just could take a point over here, say a little bit less than 1. We could take a point over here a little bit greater than 1. Calculate dy, calculate dx, and then that ratio would be this constant rate, which we call the rate of change at the moment, x equals 1. Okay? So here we go. So function f, that's the one I just showed you. Down here, this is just what it looks like for about 1.5 seconds. Relates Usain's distance from the start, dependent variable, to the time since the race started, independent variable. The displayed graph of f near x equals 1 seconds is essentially linear from 0.99 seconds to 1.0 seconds. So there's that version. So here I'm showing the moment from 0.99 to 1.01 seconds, and it's essentially linear. So we can use the idea of constant rate of change within this small time frame, and just assume that it is, because it's so close to constant rate of change when we get this small moment around 1. Okay, so now we're going to imagine x. Imagine x increasing from 1 second to 1.06 seconds, and I'm showing that here in the animation. Okay, simultaneously, the distance from start changes from 3.4882 to 3.5251. Okay, so the ultimate question is what is his speed at the moment 1 second? But before, and we just talked about how to do that, but I want to do another exercise first, and that is I want to practice these different elements, both their values and symbolic. So for each of these items, 1 through 6, you're going to identify the value associated with it, given the information, how it's represented symbolically, each of those things, and then how it's represented on the graphs. So for each one of these, 1 through 6, what's the actual numerical value? How do we represent it symbolically? where do we see it on these graphs? Okay, we're not going to use y at all. We've got a function. We've got a function f. So everything can be done with x and using our function. So no y's. Okay, number 2, symbolically, how do we represent that initial value of the dependent variable? Should know this. How do you symbolically represent that? Some people are saying it. F of 1. F of 1. How many people got that before we said it? Not enough. The function notation gives values of the dependent variables. Huge. This is huge. Remember doing that a couple weeks ago? This is huge. Function notation gives values of the dependent variable. F of 1. Which value of the dependent variable is it? It's the value of the dependent variable when the independent variable is 1. When the independent variable has a value of 1. Okay, the differential in x, the value. .006. Units on that. Seconds. Okay, symbolically. Okay, yep, good. I heard dx. I did not hear, so common, last students will say d of x. It's not d of x, but I heard dx. That's right, dx. Okay, differential in f. What's the value? Someone got .0368. Is it right? 0.0. Is it 368? Units on that? That's a change in what? This is a change in distance. Is he 0.0368 meters from the start line? No. What does this number mean? His change. Starting from 0.3482 meters from the start line, he changed that much. That was how much his distance increased. Okay? Got it. Keep working on the difference between the value of a variable and the value of a change in the variable. Okay? Symbolically. So we can use df, okay? F is the name of the function, but we can use df to mean a change in the dependent variable. It's okay, all right? It's okay. We can do that. So df. Okay? So what's the moment in question? Oh, let's talk about some on the graph. What about the initial value of the independent variable? Where's that represented on the graph? Basically, x equals 1. How do you see that in the graph? Do you see that here? Do you see it here? No. Where do we see x equals 1? X-axis. So when we're talking about how is x equals 1 represented, it's represented right here. And also, so this is the same graph on both sides, right? So that's question 1. That's how graphically x equals 1 is represented. It's represented by a spot on the x-axis. Okay? What about the 3.4882? Is it represented right here on the graph? 3.4882. No, that's the correspondence point. Where is the number of meters 3.4882 shown? Here. Okay? It's over here. That's where we look for, right there, is how the number 2 is represented also over here. Does it make sense? So what's represented right there? The correspondence point. The simultaneous values of the 2 variables taken together. That's represented at the point. But if you're just talking about one value, those are represented on the axis. Those are represented on the axis, either the horizontal axis for your independent variable or the vertical axis for your dependent variable. Okay? So the differential in x represented on the graph. How is it represented in the graph?
Arrow.
Okay, good. Which arrow?
DX is the one that's going to the east.
Yep, the horizontal one is our dx. This is dx. Now I'm showing dx changing because it's important that we remember that dx is a variable. So in my animation, dx changes from what to what? What does dx change from in the animation? From what to what? I'm hearing from 1 to, is that right? From 1 to. Nope, dx is not a value of x. X starts at 1, but what does dx start at? 0. So when the arrow starts emerging from here, dx is 0. The change is 0. It's not 1. It doesn't start from 1. It starts from 0. And then the maximum value of dx in this animation is 0.006. So dx itself is changing from 0 to 0.006. As x changes from what to what? X changes from 1 to 1.006. So as x changes from 1 to 1.006, dx, the change, changes from 0 to 0.006. All right, so of course, df is shown by the little vertical arrow. So now let's go ahead and freeze the situation for our specific. So now this would be freezing it for this situation I set up for you, okay? dx is the 0.006. df is the corresponding change in distance from the start. Okay? What's the moment in question? So any questions about 1 through 4? Values, symbols, or representing on the graph? All right, what's the moment in question? What's the moment in question? What did we say? Looking at the left graph or the right graph? Right graph is showing us the moment. What moment are we talking about? 0.99 to 1.01. Okay? Or you could have said 0.995. No, you actually can't, because you have to be, it's got to be something greater than 1.006. So the clear choice here is, the moment is, it's an interval, say, from 0.99 to 1.01. And remember what we said. How does dx compare to a moment? Dx changes within a moment. And that's exactly what we're seeing here. The moment is kind of everything I'm showing on the x-axis in this right graph. All the way from 0.99 to 1.01. And then within that moment, we're letting dx increase here to have a value of 0.006. So dx changes within a moment. We don't really have a anything symbolic for the moment. Is Morgan here? Do you agree? There's not really any symbolic way we have of expressing a moment, right? Just the interval. Yeah, just the interval. Okay. All right, and so then what about the rate of change at this moment? What's the value of the rate of change? Okay, let's symbolically first. How about symbolically first? The rate of change is, df divided by dx. That's how you can symbolically, or m, we call that m, right? So either way, df over dx or m. And so then we're finding the change in F. So we're just going to take the 0.0368 divided by the 0.006. What do you get? 6 and 2/15. How about a decimal? 6 point. Okay, what's the units on that? The units. She wants meters per second. Agree with that? Okay. Anybody have a question? Yes, please.
Are there any questions on moments on tonight's
Nope.
test?
Nope. Okay, let's press on. Any questions on this screen? So now I'm going to give you a similar situation than the next screen for at 0.4 seconds. So earlier, 0.4 seconds, but different information that you're given and different things that you're finding, okay? So here's the next situation. So the function f, same function. We've got the same independent, dependent variable. Now I'm going to say Usain's speed at the moment x equals 0.4 seconds is 3.04 meters per second, when his distance from the start is 0.702 meters. Okay? We're going to do the same thing again, but now you've got different information and a different goal. Okay? Different goal, which is the goal is Usain's final distance from start. And you're going to do it twice. Once for final x being 0.408, and once for final x 0.413. So let me start the animation. So now we're looking at a moment at 0.4, a moment at 0.4 seconds. I'll freeze the animation at the situation in question, okay? The situation in question is that we're at x final. Is that in the right place? 6, 7, 8, yeah. So now I freeze the animation for this first situation. X final is 0.408. Is it clear now? Okay, go. Question? Yeah, and this is great. Yeah, right now. Uh-huh. Exactly. Yeah, that's what we've been doing the last 2 weeks. Got it?
Yeah, sorry.
Yeah, it's okay. It's okay. It's like you have to. It has to be on the ready, right? So that's what we're doing. Okay. Symbolically represent the initial value of the dependent variable. Did we do better this time? Say it. F of 0.4. How many people got it this time before we said it? F of 0.4. Better, but not good enough. Values of the dependent variable are expressed with function notation. Values of the dependent variable are expressed with function notation. F of 0.4. Where do we see that on the graph? Where do we see this f of 0.4 equals 0.702 on the graph? Here? Oh. Oh, over here. Here. I'm sorry. I should have said here. No. Here. Right there. F of 0.4. Right there. 0.702. That's where we see f of 0.4. Okay? The differential in x, of course, is dx. And what's its value here? 0.008 units. Is that 0.008 seconds since he started running? No, that's the change since 0.4 seconds. That's the change since 0.4 seconds. It's shown right here. The change. Differential in f. df. Okay, so This is where the rubber meets the road. Who got DF? Raise your hand if you got DF. Should be everybody. This is the most important theme in the last week and a half. The change in the dependent variable. Do we have constant rate of change?
Yes.
Yes. Therefore, the change in the dependent variable is our constant rate times the change in the independent. How many people got it before I did it? Okay. Good practice. You figured it out. Yeah. Okay. So this has to be at the ready. We have constant rate of change. You want to change in the dependent variable. We have the change in the independent. We know that given any change in the independent, the change in the dependent is m times as much, right? M times as much. So we can do our 3.04 times what? Times the change in x. Just barely got it. And what does that come out to be? 0.0243 units on that? Is that how far he is from the start line? What is that? How much his distance changed since 0.4 seconds? It's not his distance from the start. This is a change in his distance from the start. Okay? How do we get his final distance from the start, which would be, so how, symbolically, so this is great, last question here. Just symbolically, how would we just symbolically express his final distance from start in this situation? F, good. F of 0.408. Do you see it? That's how we express it. F of the final time, 0.408. Okay, and how do we calculate it? Again, do you have this tool at the ready? Are you ready to use it? We want a final distance. How do we calculate it? Everything's okay. Everything's okay. All right. Don't want to lose what I've written. Good. Okay. So, final value of the dependent variable equals initial plus the change. Initial plus the change. Initial was? Remember this? See, this is important. That's why we worked on it. So initial, which would be f of 0.4, is our initial, plus how much it changed. So I could write df here, or I could write, what else could I write? M dx, or df. And that change we just found, 0.243. The final value of a quantity is the initial value plus the change. The final value of the quantity is the initial value plus how much it changed, and we can calculate how much it changed using constant rate of change, m dx. And what do we get? I think that's right. And what's the units on that? Distance from the start? Distance from the start? Yes. This was the final value of the dependent variable. This is distance from the start at 0.408 seconds. Initial plus the change. So this is not a change. This is a true value of the function f, or distance from start. That was the change. The moment, you could have said 0.4 to 0.415. Moment was the interval from 0.4 to 0.415, within which we were changing dx. Questions on this very important slide? See how all this stuff that we've learned is important, like it's all building. We need everything we've done before. Function notation, constant rate of change, final equals initial plus change. Okay, all that stuff. So we've carefully chosen what we've done in the first 4 weeks, to be the stuff we need the most as we get into the calculus here. We're getting close. We're close to calculus. Now that we're looking at small changes. Okay? Perfect. All right, last chance for questions before top hat. So you could, for practice, you could go to the screen when it's white, so go back to the video, and when there's nothing written on it, and do it all again for 0.413 seconds. Practice it again for 0.413 seconds with a blank screen in the video. One question, yeah? It's DF. It's DF.